think the screen is on now. Let's begin. Well, the goal for today is to go through section 3 of Hatch's notes, and the title of the section is the easy case, which means it's easier than the next case, but it's not exactly straightforward. So let's see what we can do. Namely, we want to prove I will first write some statements, and then I will explain or recall the notation. The first statement is, by the way, let's assume that k is greater than 0. I will in a minute. I will explain what this k is. Moreover, this group is isomorphic to the embedded cobordism group of d minus k. Oriented submanifolds of oriented and compact of Rn minus k. Okay, I will in a minute. I will explain in more detail what this group actually is, and it's similar, although not identical to the usual oriented cobordism group, which is basically the same group as this one, if we let n be large enough. Okay, so this is the first part, and the second part is Okay, let me know. Okay, the second part, I will explain everything, not just B. I will try to explain everything, or at least as much as I understand myself. Okay. Now, what is C naught n k plus 1? Well, what is naught? Well, naught stands for the component of the empty set. Okay, what is B n plus m n k? Well, this is the Moore version of C and K. And well, B is the classifying space. We will review its construction in a minute, but very briefly, it's the same as the classifying space for groups, except we do the same construction for monoids, not for groups. But if we recall the construction of the simplicial classifying space, the phase maps only involve multiplication. They don't use inverses, and the construction makes sense for monoids as well.
No, I didn't mean the D. I mean, omegas of D minus k. What is the D?
Well, D is the dimension of the manifolds we are primarily interested in. Mostly we will so for the Madsen-Weiss theorem. No. We want to understand some mapping class group or some stable mapping class group or something of that kind. So in our case, well, the cases we'll mainly be interested in are d equal 2 or d equal 0. Although later on we will probably say something about arbitrary d. Well, d equal 1 is not particularly interesting, but higher d's are interesting, and we'll probably say something about that. Anyway, okay. So this is the goal. Let's see what. What all the letters mean. Okay, the screen in room 110 is very large. So I can squeeze the explanation on the same screen, and I hope it is readable. If it isn't, please let me know. Okay, what is C and K? Okay, so this is the space of submanifolds of Rn, which are properly embedded, so they're closed as topological subspaces. But moreover, we require that, in fact, they live in Rk cross 0, 1 to n minus k. And one particular thing we will need is if we take any element of this space, the projection to Rk is proper. Now this is a kind of a monoid, but not exactly a monoid. Why? Because the addition or the operation is only associative up to homological. And what is the operation? Well, well, it's rescaling and juxtaposition in in the k plus first coordinate. And well, we basically do the same thing as we do when we multiply loops, and the same sort of problems occur. Namely, the operation is not strictly associative, so we may turn it into an associative operation by considering a more version in which we allow the k plus first coordinate to be between not necessarily 0 and 1, but 0 and something, and then we get a strictly associative operation. Are there any questions, remarks? Does this definition coincide with what happened last time? Okay. Now let me explain the cobordism group. Well, the embedded cobordism. Well, the embedded cobordism group. I think the well, most of this description is probably self-explanatory. Please let me know if it isn't, but I will say. I will just say the following thing. What does cobordant mean? Well, suppose we have two submanifolds of dimension n minus k, and which live in R, d minus k, which live in R n minus k. We say that two manifolds are embedded oriented cobordant if there is an oriented W inside 0, 1 cross R n minus k, such that the expected properties hold. Namely, the boundary of W is inside 0 cross R n minus k disjoint with 1 cross R n minus k, and the top boundary component is M1, the bottom one is M2, and the orientation is induced from W. Minus M is the reflection of M with in a hyperplane. How to prove that M disjoint union with minus M is 0. We take W W to be a cobordism which has the shape shown on the board, and this is a cobordism between M disjoint with minus M and the empty set. Okay, Are there any questions, remarks, comments, criticism, and so on? And by the way, am I right that everyone can hear me?
Yeah, we can hear you.
Okay, if you don't disagree with something, then please let me know. Don't keep it to yourself.
So maybe you can say something about the relation of this definition to the usual definition of cobordism inside of a topological space between two manifolds.
Well, the only difference is that we require all submanifolds and cobordisms to live in some Euclidean spaces. So if I fix D and let n be large enough so that it is twice the dimension of so if n is twice the dimension d, then basically we get the usual cobordism or oriented cobordism groups. And in general, those groups are not isomorphic to the usual cobordism groups, but when n is large enough, they are.
For example, like some types of nodes slice between the common to zero in this sense and some not.
Yes, well, as slice nodes basically, not very good example. There are basically every circle bounds a disk. There's no argument about this. But then suppose we take a knot in the free space. Does this knot bound the disk? Well, the answer is very rare, if and only if the knot is trivial. But what about the disk in the force space? And then, as Dennis tells us, this is true if and only if the knot is sliced, and there are two versions: smoothly sliced or homologically sliced. Let's not go in. Anyway, there are sliced knots, there are knots which aren't sliced. And starting from dimension 5, I think 5 should do, starting from dimension 5, every knot in the 3 sphere bounds the disk in the 5 sphere. 5 or maybe 6. Anyway, starting from a dimension which is high enough, one can embed the disk, the bounded disk in the sphere, and but in general, if the dimension is not big enough, it's not possible. Okay, does this make any sense? Okay, well, are there any more remarks, questions, and so on? Okay, well, in this case, let's wipe the slate clean, but let's try to remember what we're trying to prove. By the way, it's not exactly a slate, but it doesn't matter. Okay, let's prove the first part. Let's prove that pi naught. Now we understand all ingredients in this statement. So we basically we know what we're trying to prove. We don't know how to prove it, but we know what we want to prove. Okay, in particular, phi naught is a group. Okay, well, let's and moreover, this is not just any group; it's isomorphic to this group. Okay, so suppose no. Well, suppose I have a manifold M inside C and K, then projection. Well, then M lives in Ri cross 0, 1, 2, and minus no. N minus K, and the projection to RK is proper. Well, let's assume that 0 is a regular value. Let's call this projection P. The map we want to construct is as follows. We take M into the cobordism class of the preimage of 0. There's there are a few things which are straightforward to check. Well, first of all, we assume that 0 is a regular value. And by the way, does everyone remember what a regular value is? Okay. Now let's try to review this. What is a regular value? Okay, does anyone remember what a regular value is?
The derivative must be non-degenerate.
Well, a regular
The
value.
pre-image, the differential at the pre-image of that value must be non-degenerate.
Yes, a regular value is something which is not a critical value. And what is a critical value? Well, a critical value is the same as the image of the image of a critical point, and a critical point is the same as. And by the way, there are several definitions of a critical point, but for our purposes, the one that works is this. The differential at this point is not subjective. And the preimage of a regular value is a submanifold, which is why this definition makes sense. Otherwise, we just get something here which may or may not be submanifold. And a standard argument shows that the submanifold M node may depend on what exactly we do to make sure that 0 is a regular value, but the cobordism class does not. So the cobordism class is well defined. Okay, now this map is a group homomorphism . Why? Well, we have operations on the left and on the right, and both are just taking the disjoint union. So the operations are the same. Okay. Now we want to prove that this homomorphism is an isomorphism. Let's prove that it's surjective. no, blah 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 blah. Well, the surjectivity is easy. Surjectivity is easy. M naught cross R n minus k goes to the class of M naught. No. No. Hold on. I want to project. I want to project onto. I want the projection onto RK to be proper. So what should I put here? Is it M naught cross Rn minus k or Rk cross M naught?
I'm sorry, I don't understand. Why is it not M naught across 0, 1 to n minus k?
Say again. I didn't catch it.
I don't.
Гриша, я не расслышал, что вы сказали.
Yeah, I thought that maybe we should take M naught times the segment 0, 1 to the power n minus k, but I'm not sure.
Well, we want here we want something which would give me M naught after applying this this procedure.
Then maybe I should just take M naught itself, no?
But then I also want something of the right dimension. M itself has dimension d, but then when I take the preimage, the dimension drops, and the preimage of basically of 0 inside R count. Now let's in particular M naught should be where? Inside Rk or inside Rn minus k? Well, what does it mean to take the?
It should be inside Rn minus k.
Well, exactly. It means to take the intersection with 0 inside Rk cross Rn minus k. So what I should put here is instead Rk cross M naught. And well, this manifold this manifold goes back to the class of M naught under this procedure. And now a trickier point. We want to prove that the map is injective. No. Well, in other words, suppose we have M which goes to M naught, and suppose that the class of M naught is the same as the class of M prime naught, which is the image of M prime. Now we want to prove that M and M naught can be joined no, sorry, M and M prime can be joined with the path in Cn chi. Okay, well, let's try to construct this this path. Well, my first claim is that M is in the same path component as Rk cross M naught. Why is this? Well, let's remember that M lives in Rk cross 0, 1 to the n minus k. So in particular, the first k coordinates of an element of M can be arbitrary. And what we do is we do a radial expansion in the first k coordinates. What does this mean? Well, this means I take m, and then I apply for every t from 1 to infinity, I apply the rescaling with factor t to the first k coordinates. And my claim is, and every time I do this, I get some submanifold of Rk cross 0, 1 to n minus k. And my claim is, as the scaling factor goes to infinity, the limit exists, the limit in this space, and moreover, it is Rk cross cross m naught. So we get a path from M to a simpler manifold, which only remembers what happens near the preimage of 0. M could be very complicated. We forget everything, and we forget everything, but we obviously get the different elements of C and K. All we know it's in the same path component, and then we get a simpler manifold Rk cross m naught.
Is this on the manifold on the topology report? It's weak in topology, it does not exist.
There is no the weak topology. There are several versions.
I mean, everything.
There is the strong topology and the weak topology. But let's try to remember which topology we use. Well, first of all, we need to topologize elements of C and K are not necessarily compact. They are closed, meaning they're properly, they're not necessarily compact. We first apologize compact submanifolds of a closed wall. And here or more precisely, we topologize the set of all submanifolds of a closed wall such that the intersection with the boundary is transversal, and the boundary is intersection with the boundary of the wall. Anyway, we'll take a closed wall. We allow manifolds with boundary. We require that the boundary of all those should be inside the boundary of the wall, and the intersection with the sphere, which is the boundary of the wall, should be transversal. And then we use the Witten topology, and it doesn't matter which one we use, because in that case, all sensible topologies coincide. The way, normally we consider the Witten topology on the space of magnets. But here we have the space of manifolds. What do we do? Well, there are several ways to proceed. Well, my favorite one is to consider consider a metric. Some remaining metric on the wall, and then consider a modification of the Hausdorff metric on the set of all compact subsets. well, the Hausdorff metric gives us a C0 approximation, and then we're taking by taking jet bundles and so on, we can take higher derivatives into account, and we get a topology on the set of all compact submanifolds. I'm sure there are other ways, but in the compact case, everything, all possible, all sensible topologies are the same, whereas in the non-compact case, it's not true. Anyway, we first topologize reasonable compact manifolds of a ball. And then we take all balls centered at 0, and then we let the radii go to infinity, and we use open subsets obtained from each of those balls as a basis for the topology. So, in particular, a sequence of manifolds tends to another manifold if and only if for every finite ball the intersections with this ball tend to the intersection with the same ball. And this is why we are allowed to do this trick, because for every finite ball the intersections will go to the intersections of this of the family we get when we deform M will be the same as the intersection, or will tend to the intersection of this thing with the same ball. Okay, does this make any sense? Денис, Гриша, значит, понятно ли были вот эти объяснения, или они совершенно непонятны, или они вообще не, значит, не... Значит, well, we did okay. Значит, Денис, еще раз, я правильно понимаю, что вы предлагаете это написать?
Нет, не думаю, что того, что написать на доске станет ясно, потому что требует внимательного рассмотрения, что информация не очень возможно. Но может быть, что кто-то это внимательно проверит.
Ну, нет, Денис, это безответственный подход. Нужно самому это проверить.
Ну, да.
Значит, еще раз.
Что в компактном случае все пространстве многообразие одинаково.
Значит, дальше у нас появляется семейство, которое мы хотим проводить топологию. Значит, оно параметризовано понятно чем. Значит, дальше, в общей топологии первого курса были условия. Когда мы можем проводить, топологию в данном семействе можно проводить всегда, значит, в понятных условиях, утверждение, что там открытые множество топологии, они будут в точности там объединениями или пересечениями вот этих вот множества семейств. Значит, и там есть условия для того, условия для другого.
После того, как мы топологию на шаре, дальнейшее это стандартное, конечно.
Что значит на шаре стандартное?
На многообразие шара.
Да, значит, а вот многообразие шара, значит, как я уже говорил, значит, есть разные способы действия. Вот, значит, мой любимый с помощью метрики Хаусдорфа. Значит, помните ли вы, что такое метрика Хаусдорфа? Хорошо, значит, тогда, значит, это ценой приближения значит, интересующей нас топологии. Но она совершенно не помнит простая, что производная. Хорошо. Значит, но у нас значит, есть расслоение, значит, расслоение струй, точнее, вот так, у нас есть расслоение ростков под многообразие такого-то порядка. Ну хорошо, значит, рассмотрим значит, это вот расслоение ростков под многообразие такого-то порядка. Ну, конечно, нет. Значит, дальше любое подмногообразие дает сечение этого расслоения, значит, но не все сечения приходят из подмногообразия. Иногда приходят, это называется шприц. Но сейчас не важно. Значит, какие-то приходят, какие-то не приходят, но это не важно. Но сечение, значит, это все равно будет, ну, скажем так, даже здесь уже никакие там курсоры не нужны, по-моему, если у нас есть, и нет, все-таки нужны. Значит, вот, отождествим сечение с его графиком.
Конструкцию топологии я понял. Остается не очень ясно, почему она хорошая, и нет. Да, по-моему, понятно, почему на этом работает обычная конструкция индуктивного предела, это понятно.
Значит, ну,
почему она хорошая, не очень ясно.
Ну, слушайте, зависит от того, что такое хорошее.
По-моему, эта вещь не очень уважает позицию отображения, мне кажется, если мы захотим на этом поговорить.
Ну, с композицией отображения, там, сейчас у нас, нет, в общем, по-моему, там все, в общем, там все разумные, там условия для этой штуки, по-моему, выполнены. В общем, и более того, я сейчас предлагаю не погружаться в это дело глубоко, но... Нет, это действительно важный вопрос, но, значит, Денис, я предлагаю сначала продумать его. Если там обнаружится проблема, давайте их обсудим. Значит, если обнаружится темные места, давайте их тоже обсудим. Но если ни того, ни другого не обнаружится, то предлагаю идти дальше. Ну, значит, может быть, у той же топологии есть еще несколько конструкций, значит, которые окажутся эквивалентными. И значит, дальше возникает вопрос, как это доказать. Ну, как это можно доказать? Значит, но это требует не бесплатно, а требует каких-то усилий. Так, хорошо. Grisha, Grisha and everyone else, does this explanation make any sense at all? Гриша, если вы что-то сказали, то мы этого не слышали, по крайней мере, я.
I guess it makes sense.
Okay. Well, well, if it doesn't make sense, please let me know. Well, the same argument works. For n prime and RK cross n prime naught, and all we need to do is to construct a path between m naught and all we need to do is to construct a path between RK cross m naught and RK cross m prime naught. here we use the fact that M naught M prime naught are concordant which means there's this W inside R. There exists a W inside R n minus chi such that, and well, let me draw this W. Well, there exists a cobordism from M naught to M prime naught, and then what? Then we and then we'll okay. Let me now extend let me extend W by one infinity cross M naught and minus infinity 0 cross M naught prime. Okay. Now, okay. Now let's see what happens. What happens if I translate W to minus infinity. What will the limit be? Well, it is clear from this picture that the limit will be R cross M naught. Well, the limit in the space of n minus k plus 1 R n minus k, sorry, R minus k plus 1, and here we have D. Minus k plus 1 submanifolds of Rn minus k plus 1. Well, similarly, if we translate W to plus infinity, the limit again in the same space is what is R cross M prime naught. Okay, well, this is clear from the picture. Now what? Well, now I can multiply everything by R k minus 1. So let me just do this. And here I get again Rk minus 1. So everything gets multiplied by Rk minus 1 on the left. And we get the following thing. If we take W cross R k minus 1 and translate it to plus infinity, the limit is this, and if we translate it to minus infinity, the limit is this. Basically, one of the limits is this. The other limit is this, and somewhere in the middle we have R k minus 1 cross W. Okay. Where W is a cobordism between M naught and M naught prime. Okay, does this make any sense? Note that all translations happen in the coordinate which corresponds to I. So all translations happen. So the orange translations happen in So the orange translations happen in the kth coordinate. So we remain in C and K. Okay, does this make any sense? Well, orange translations means what we do after we multiply everything by rk minus 1. Does this make any sense at all? Значит, let's go back. We constructed a map from this group to this group. We want to show that this map is an isomorphism. It's more or less clear that the map is surjective. Now we want to show that it is injective. What does this mean? Well, this means if we have two elements, if we have M and M prime which have the same image, then they should be in the same path component of this space. Well, we first join M with RK cross M naught, and we do the same for M prime and RK cross M naught. And then we join these two. And to do this, we need a cobordism between M naught and M naught prime. And we get some path, and my claim is this path stays entirely within C and K. And so my claim is that both those manifolds are in the same component of C and K. Okay, and this proves the first part of what we wanted to prove. And then we will need to prove the second part. But before we do, let's have a break. Okay. Are there any questions, comments, criticism, and so on? Then let's have a break. So break. Okay. Well, let's continue. Well, next task is to prove this this equivalence, namely the classifying space of the Moore version of this is the Moore version of C and K, and this is the component of the empty set. The next step is to prove that these two are homotypically equivalent. And well, the plan is to construct a map from the left-hand side to the right-hand side, and to show that this map produces an isomorphism of the homotypic groups. So, in fact, what we will prove is a weak equivalence, and then it's probably true that the space on the right has the homotypic type of the CW complex. The weak equivalences are the same as strong equivalences, but one needs to be careful. There are sometimes surprises in questions of this type. Well, first of all, let's review what the model for VM, which we saw a couple of weeks ago. Okay. Now the construction is as follows. We construct a semi-simplicial space starting from M. Now, to do this, I define the face maps. Well, basically, the first and last one, just delete the first, respectively, the last element from the sequence, and all the rest are given by the multiplication in M, and then I consider the geometric realization of this semi-simplicial set or space. And by the way, a monoid contains a unit. Basically, it's part of the definition of a monoid. So, in fact, there is a way to turn this semi-simplicial space into a simplicial space, and the question is, does this change the homological type of Bm? And the answer is, if M is sufficiently nice, it doesn't. And I've forgotten what exactly sufficiently nice means, but if you are interested, you could look it up in one of Siegel's papers. I've forgotten the name of the paper, but again, if you're interested, ask me, and I'll find it. But for our purposes, let's forget about simplicial. Let's do semi-simplicial. It will suffice for our purposes. Okay, now do the words geometric realization of a semi-simplicial space make any sense, or would you like me to review this thing? Simon. Okay. Okay, so unless there are explicit requests, let's assume that we all know what this tilde means. Okay, let me try to save and see what happens. Okay, I've managed to save one slide, which is not much, but it's better than what happened at the first attempt. Anyway, we'll take these deltas. We then construct a semi-simplicial space using the deltas, and we'll say that Vm is the geometric realization. Okay, now now we want to apply this to our case, m equal b and k. Sorry, m equal m and k. We do that, and now we want to construct a map. it follows from our construction of BM that it suffices to define the map on we'll define the map on each product delta P cross NP and check that the result agrees with the equivalence relation. let's make a naive attempt, and then we'll see that the naive attempt doesn't quite work, and we'll try to fix it pushing the problems to infinity. So the first attempt, which will not work. Let's remember what MIs are. Each MI is a manifold. Is a manifold where? Let's see. So R chi minus 1 cross chi, here we'll so AI is greater than 0, and the manifold is is inside RK cross, well, the interval 0 AI cross the product of the remaining intervals, which are 0, 1. Let me let me take the MIs, the manifolds, and stack them together in the k plus first coordinate. And then let's take the result. The result M unfortunately does not depend continuously on let's see. So in this construction of M, I only use the elements of the monoid, M1, etc. But I did not use the weights. Let's just state the fact that this M this M does not agree with the tilde. What does this mean? This means if if I let one of the W's, or more precisely, W naught, etc. WP are the barocentric coordinates of an element of delta P. What happens when this element of delta P tends to an element at the boundary? Well, it depends. It depends on which face this element of the boundary belongs to. By the way, did we just lose everyone? Let's see. Maybe not. So let's. No. Okay. Well, I think something happened, and that I don't know whether or not it's what's supposed to happen. Anyhow, let me say it again. Okay. Cancel. Anyway, okay. Well, something happened, and I don't know what exactly happened. By the way, Simon, can you is the seminar still on?
Yes.
Okay, so it looks like we're still online. Anyway, let's see what happens when the element of WP tends to an element of the boundary. If this element converges to one of the intermediate faces, basically nothing happens. We simply replace a couple of manifolds somewhere in the middle by their product, which agrees with this definition. But when this element tends to an element of phase 0 or phase P, bad things happen. When W naught goes to 0, the first manifold suddenly disappears. When WP goes to 0, then the last manifold suddenly disappears. And moreover, when W naught goes to 0, then the manifold M suddenly jumps from oh, sorry, by the way, this is supposed to be 0. No. Undo. So the manifold M suddenly jumps to the right. No, to the left. Two problems. The most important problem is that some components disappear when the first barocentric coordinate or the last one go to 0. Well, so what do we do? We do what we did a few times before. We push the first and last component to infinity as or both of them as the weights approach the corresponding faces. So these are problems. The solution is basically we we define a function on the simplex delta. I don't know. Let's call this function alpha. I need two functions. Alpha. Okay, I define two functions. Alpha naught and alpha p. Okay. Well, I don't want to. No, I don't want to define those functions. It's going to be a mess. Well, in Hatch's notes, he does attempt to write an explicit formula for this, and it's I'm not sure it makes anything any clearer. Well, let me give a hand-waving argument. We Okay, so this is a way to handle the main problem, but there was another problem which involves m jumping to the left. Let's see how to handle this this problem.
Выбрать другие координаты на БН, именно на пространство, назначенных распределенного отрезка с конечным носителем, когда все эти пихтовые бесконечности довольно просто решаются как фиксацией гомоморфизма R с внутренностью отрезка, и там как бы точки идут ровно туда, куда они должны ехать.
Да, но если сейчас там пробовать писать явную формулу, то ничего не получится. Ну, в общем, значит, будет хуже, значит, хуже или лучше. Okay, so the trick which could be used to prevent m from jumping would be not to use the interval from 0 to the sum of the ai's. Sorry, but the way I think I messed it up. I think it's supposed to be I, comma AI. No. Okay, I'll okay, I think this formula is correct, but let's ignore it for the moment. Let's focus on vanishing components. This is a bigger problem. So the trick is to push the vanishing components to minus infinity and plus infinity in the k plus first coordinate, as yes, so as w okay, let me try to think some more about it. Basically, as w approaches, as w naught approaches 0, the zero's component should go to the empty set, and all the other components should stand still, or almost, meaning the union should converge to the same union defined for the previous phase. And well, similarly for the p component and all those all those pushes to infinity should happen in the k plus first coordinate element. Let's have a look at this explanation and see if it means anything at all. Так, имеет ли какой-нибудь смысл это насчет объяснения?
Сказано, и вполне, но мне кажется, я смог бы привести это новый язык, чтобы стало понятно.
Так, ну хорошо. Well, Dennis says he sort of agrees with this argument. Not necessarily with the exact wording. Okay, I will try to will try to draw what I just said, but I'm not sure if it's any help. So basically, we as W naught goes to infinity, we push M1 more and more to the left in the K plus first coordinate, and we keep the remaining manifolds away from infinity. The remaining, meaning the ones strictly between M1 and MB. Similarly, if NP, if WP goes to infinity, we do the same with the last manifold, while keeping the rest fine. And then if both M1 and MB go to infinity, by the way, no, I think a better way to draw this would be to do this. These two are far away, and okay. To summarize, we get a map sigma, which is well defined. But we also need to prove that sigma induces an isomorphism of the homological groups. This is not it. So we want to prove that sigma induces an isomorphism of the homological groups, and well, there are two things to prove. Namely, we need to prove that the map is surjective and injective. Let's prove that it's surjective. And suppose we have a map from Dn to C. C and chi, such that the boundary goes to the empty set, and we want to somehow prove that the map is homotopic to well, to something which comes from Bm. Okay, now. Well, let's first focus on. Sorry, it's n k plus 1. Oh, by the way, let me use a different letter here, because this n is well, not the same as the dimension of the ambient space. Let's call this this one q. Okay. Okay, so we have let's fix a point inside the disk and see what happens with this. Let's see what happens with this manifold MT, which is the image of T. Okay, let's call it just M. Well, this time we have something that properly projects onto RK plus 1. Let's first consider the case when when d is strictly less than k plus 1, then we'll do something, and we will then try to repeat the same when d is large. Okay, so well, d is the dimension of M. Okay, now if d is small enough, then what? Then, well, let me call this map P. Then P of M, this is some small disk, which I want to think about as a product of a disk and RK and a closed interval in R. Okay, here I take a projection from M to arc chi plus 1, and the coordinates of the image can be arbitrary. So I rescale M, and I want let's recall what we want to do. We have this map, and we take some manifold M, which is the image of an element of the disk. Now, what is this M? We don't know. There is no reason to hope that this M is the disjoint union of some number of manifolds juxtaposed in the k plus first coordinate. M could be arbitrary. So first of all, we want to cut it into pieces which are disjoint in the k plus first coordinate. And that's what we do. Okay, what do I do? I rescale M. In the k plus first coordinate. Brilliant. And I rescale M to infinity. So that okay, no, it's more complicated. I don't want to rescale all of them from 1 to infinity. I use the following thing. Far away from the projection of far away from if the k plus first coordinate is far away from J, I do nothing. If it's close to the middle of J, then I rescale hold on. Sorry, not in the k plus first coordinate. In no, in the first k coordinates. Let me erase this.
last coordinate to stage this disk universal intersection.
In the first k coordinates. Yes. So I want to rescale. I want to rescale this component, but depending on this component. If the r coordinate is far from j, nothing happens. If it's in the middle of j, I rescale from 1 to infinity, and then I damp the scaling more precisely. I damp it near I damp it near not I damp it near the ends of the endpoints of the interval j. Okay. Now let's see again what happens. I want to get rid of. I want to get rid of. I want to. I want to connect M inside Cnk plus 1 with something which does not intersect. So the new manifold. Does not intersect R chi. Does not intersect the slice does not intersect the slice which is does not intersect any of the slices which are described well, which are defined here, where G prime is some subinterval of J prime is some subinterval of J. Okay. In other words, M, when we project it to Rk plus 1, misses some balls. And then I got it along along a hyperplane which is given by the first coordinate, no, the k plus first coordinate being equal to I for a some interval of for a inside some subinterval to J of J. Okay, do people want me to draw a picture? Someone? Okay, well, let's try to draw a picture. Okay, okay. Okay, let's say that this is RK, this is R, and this is R n minus K minus 1. Okay, now suppose I have a curve. Which is M. Well, I projected I project this curve to R k plus 1. Since the curve is one-dimensional and k plus 1 is two-dimensional, in this case, the result misses the product of B and J. Okay, now okay, now what do I do? I want let's see. I want the entire M to miss what? Let me think a little. Yes, I want the entire M to miss J times R to miss RK times J. Well, it's not possible, but I can do this for. Okay, I'll change the drawing slightly. Okay. Okay, so I want the entire RAM to miss J times. So we want to miss this RK cross J. Cross the remaining factor n minus k minus 1, not just and what do? We push depending on okay, so if the r coordinate is close to the boundary of J, nothing happens, and otherwise I replace well, the drawing is not perfect. Let me. Okay. The drawing is not perfect, but okay. Let me explain again what happens. I take the part, or actually, the drawing is not quite correct. Let me change it. Okay, I want to take this part, which is inside some subinterval of J, and push it away to infinity in by rescaling in the k plus first coordinate. I think if I say any more about this, it will only make things worse than better. So let's recapitulate on what we did. We proved that in in this case, when the dimension is small enough, we may assume that, well, I'll just write a conclusion. When the dimension is small enough, we can cut M, well, cut quote unquote, because well, we're not exactly cutting it. We can deform M to a manifold inside this space, which is disjoint from any of the slices which are given here on the board. Now, the same is true for d greater than or equal k plus 1, but the proof is more tricky. Do we want to go through it now, or is it probably better to stop? По-моему, уже все, дальше не лезет. Денис, имеет ли хоть малейший смысл то, что происходит?
Ну, геологически, практически.
Практически не имеет. Значит,
Ну,
значит еще раз. Значит, у нас есть многообразие вот здесь. Но вот многообразие вот здесь, они совершенно не обязаны быть порезаны на куски вдоль каждой сферы координат.
Ну, мы используем, собственно, двоичную координату.
Значит, теперь мы в административном порядке берем многообразие и пытаемся выбрать такой интервал, вдоль которого оно порезано. Пока просто интервал. Какой-то один интервал, выбрали и как мы это сделали. Ну, если размерность достаточно маленькая, мы смотрим там шарик, и который не лежит в образе, режем вдоль этого шарика. Вот, если размерность большая, нужно использовать то, что многообразие конвергентно, которое получается в причине, будет конвергентно нулю. Вот, и пока утверждение такое, что для каждого многообразия вот отсюда найдется вот такой интервальчик, так что да, и там соединяющиеся лежащие в той же компоненте многообразия штрих, который лежит в том же самом, то есть которая имеет вид, который не пересекается с такими слоями, срезами. Так, ну хорошо, ну и да, и дальше, собственно, причем здесь гомотопические группы, вот это очень сейчас мы насели. Ну, здесь ну, в каком смысле на каждом шагу используется конструкция?
В каком-то смысле, да?
Ну, там не буквально, по тем причинам, которые мы уже обсуждали. Видно, что спектры, которые возникают в этой науке, они очень похожи, но не в буквальном смысле равны спектрам конвергентным. Okay, well, let's save the notes. Well, it didn't work. Anyway, let's save the notes and let's do this properly. We don't want we're not in a hurry. Let's do this thing properly, and next time we'll see what this has to do with homological groups and why exactly the map of the homological groups is so effective, and then we'll see it's injected for more or less the same reason. Okay. Well, are there any questions? Well, I don't think there are any questions. Anyway, I think I've saved the notes. Okay. Есть ли какие-нибудь вопросы? I think there aren't any questions. So we didn't prove that the map of the homological groups is either injective or surjective, but we did construct a map of spaces which hopefully induces an isomorphism of the homological groups, which is it's not much, but it's better than nothing. So we'll meet again next time. Hopefully both off and online, but otherwise it will be online. Is there anything else we want to talk about today? Well, it looks like the answer is no. So see you all, and until next week.